What if I told you there's a way to send a message so secure that no hacker, no government, not even a quantum computer could crack it ever? Well, I know it sounds like science fiction, but it's not, because that thing is called one-time pad, and it's mathematically proven to be unbreakable, if you use it correctly, of course. Today, we're going to explore how the one-time pad works, why it's theoretically perfect, and why, despite that, it's not everywhere in our everyday life. What is one-time pad? Imagine a secret message or plain text like hello. To encrypt it, we use a random key of the same length as this plain text file. And that random key, is generated once and never reused, hence why it's called one time. Now, I know that you guys might say, well, that's what we've done in the AES video, or maybe in any other video that we will do about encryption, right? We generate a random key. But the main and only difference is that the key, in this case, in this encryption function, is that it should be the same length as the plain text. Otherwise, it won't work. It won't fulfill the perfect security criteria. Now, we will look at using the XOR operation, or the exclusive OR. We combine each bit of the plain text with the bits of the key. If the bits are the same, the result is 0, and if it's different, it's 1. Let's get into it. As I was saying, at the heart of the one-time pad is the XOR operation, a OR, otherwise known as exclusive OR. It's a simple rule for combining two bits. 0 XOR 0 is 0. So 1 XOR 1 is 0. So if we have the same bits, then we're gonna get 0 as a result. If we have different bits, then we're gonna get 1. So let's try. This is a simple example that I wrote down. So we have the plain text, and these are the bits of the plain text. This is the secret key. And now this is the ciphertext, or basically the result of combining the plain text and the secret key. So we have 0 and 1 is 1, because as I said over here, if we have different bits, we're going to get 1. So 0 and 1, 1. 0 and 1, 1. 1 and 1, 0, because they are the same bits, and so on. And as for the decryption, we grab the ciphertext, we feed it the secret key, and then we unlock the plain text back again. That's basically the logic of XOR. Here is an example of the encryption. So we're going to encrypt this word hi. The ASCII value of h is 72, and in binary we represent it with these bits. The ASCII value of I is 73, and in binary we represent it like this. So we will need to turn the words or the letters into bits first. Now here are the h and the I. We do XOR with this randomly generated key. I just made that up. And this will be the ciphertext, or basically the result of combining the message and the secret key, or encrypting the message with the secret key. So we have 0 and 1. These are different, so we have 1. 1 and 0 is different, 1. 0 and 1, 1. 0 and 1, 1. 1 and 0, 1. And so on. Now, as I said, here's how we encrypt the one-time pad. We generate the random key, and keep in mind, it should be truly random, with the same length as our message. So the length of our message is 2 bytes. That's why we create the secret key with the same length, which is 2 bytes. We XOR, this is XOR, right? We XOR each bit of our message with the corresponding bit of the key, and the result, it will be the ciphertext that looks like pure noise. To decrypt, we just use XOR on the ciphertext. So we put the ciphertext, this ciphertext, we put it here. We XOR it with a secret key, and then we will get the plain text message down here as the result. The perfect security argument. This formula is the secret sauce. It means no matter which message you start with, so doesn't matter whether it is message M0 or message M1, every possible ciphertext is equally likely. An attacker seeing your ciphertext learns nothing. And this is called perfect indistinguishability, the gold standard in cryptography. But here's the catch. To achieve this perfect security, the key must be as long as the message, completely random, and used only once. If your message space is bigger than your key space, some messages can't even map to certain ciphertexts, and this breaks the math and destroys perfect security. And all of this leads to this new formula here. Here, this formula basically contradicts perfect indistinguishability, meaning that for a certain message, the probability is not zero, and for another one, it is zero. I will go through specific examples so you guys understand both of these formulas. So, this is the example. Suppose we have four possible messages, each of them 2 bits long. So, these are the four messages. The message space is basically these four things here, so these four messages. Now, we have the key space. Suppose we have only two possible keys, each of them is 2 bits long. This is the key space, so there are two keys. In a real one-time pad, keys should match the message space size, but here we are deliberately making the key space smaller to show the issue. And finally, this is the cipher space. This is basically the message, XOR key, and these are the results. And they will also be 2 bits long. And these are the possible values. Now, let's choose one of these ciphertexts. So I've chosen 00. Now, for each message, we will try to find a key that produces the specific ciphertext that we have chosen. So the first message is 00. So we have the first message 00 XOR the first key here 00. And the result is 00. Basically, we found this ciphertext. So works with key 00. Now this is message, right? Message 00 XOR key 11, because this is the only key left that we have. This and the result is 11. It doesn't match C00, right? And we do the same thing for this message, message 01. We XOR this message with key 00 and it doesn't match the result, and we do the same with key 11 and the result doesn't match. We do the same with this message. We XOR them with key 00, it doesn't match, and we XOR it with key 11 and it doesn't match. And finally, we go through message 11, we XOR it with 00 and the result doesn't match, and we XOR this message with key 11 and it works because we get the ciphertext 00 that we chose. So it works with key 11. The result, the ciphertext C00 can be produced by message 00 with key 00 and message 11 with key 11. But message 01 and message 10 cannot produce C00 with either of those keys. Now we will perform some probability analysis. And basically this will help us to understand those two formulas that I showed you before. And I will show them on the screen again. Now, so we have the ciphertext 00 and the message 00. Now, the probability of this one is non-zero because 00 XOR key 00, we got the ciphertext. So there is a key, which in our case is 00, that works, right? Normally, we wouldn't, the attacker doesn't know it, right? So there is a key that works. Now we have the probability of ciphertext 00 with this message. This is also non-zero because 11 XOR the key 11 is equal to 00. So there is a key, which in our case is 11, that works. But the probability of ciphertext 00 with having message 01 is 0 because neither 01 XOR 00 is equal to 01 nor 01 XOR 11 is equal to 10. None of them equal 00. And the same goes for this last one here. Now the contradiction. Perfect indistinguishability requires that for any ciphertext, like in our case 00, the probability should be the same for all pairs of messages M0 and M1. Now, let's choose two messages, right? The first one is, so in our case, M0 will be 00 and M1 will be 01. The probability of ciphertext 00, right? The ciphertext will stay the same. And the message 00 is not equal to 0 because K00 works. If we grab message 00 and we XOR it with key 00, we get 00. Basically, it's not 0, it's 1, right? It's a number. But for message 01, there are no keys basically work that return C00. And this case, basically the result is 0. So we have a non-zero number and 0 here. And this basically violates the requirement because the probabilities are not equal. And similarly for M011 and M101, basically for when we have message 11, this is not equal to 0, and the other one, 01, is equal to 0 because there are no keys that can encrypt 01 to 00. Now, as you guys can see here, they should be equal here. But if this side, if the left side of the equal sign is a number, a non-zero number, basically it can be 1, 2, I don't know, and the right side of the equal side is 0, they are basically not equal, thus breaking the perfect security. One last thing to note down is, if you guys remember, in the perfect security argument section in our video, I said that an attacker seeing your ciphertext learns nothing. But in our case, if the attacker were to see our ciphertext, he would understand that there are no keys that can take this message and turn it into this ciphertext. So this is a piece of information that the attacker now knows, and that breaks, as I said, the security, the perfect security, because they should learn nothing from seeing the ciphertext. If both of them, if both of these here were not 0, that means that the attacker seeing the ciphertext learns nothing because he doesn't know the probability of each of them, so he can do nothing more than just purely guess. Now, to wrap things up, I will explain a real world use and also failures. So, the one-time pad wasn't just a theory in a textbook, right? It was actually used in wartime espionage and high-level diplomatic communications. During the Cold War, Soviet agents and embassies relied on the one-time pad to send secret messages back to Moscow. But here's where things went wrong. In the late 1940s, the Soviets started reusing key material, probably because generating and distributing giant truly random keys was such a logistical nightmare. This broke the golden rule of the one-time pad: never reuse a key. American codebreakers at the Venona project spotted the reused keys, compared different intercepted ciphertexts, and were able to recover both the key and the plaintext messages. What should have been unbreakable encryption ended up revealing the identities of several Soviet spies. So what's the lesson? Even the strongest cipher is only as secure as its implementation. That's the one-time pad. Simple yet unbreakable when done right. Share your thoughts in the comments, like and subscribe for more cryptography videos. Next time we will actually try to implement the one-time pad into a program. See you then.